The least squares problem can be solved by solving what are called the normal equations. And the solution here is not a true solution to your original problem, because that's inconsistent, but instead what you're doing is finding these coefficients b and m that give you the line of best fit, the closest fit for your data. Now, this procedure is okay when we're solving small systems and we're doing it by hand. So for the typical textbook calculations you do, that'll be fine. But where we're going is that in real life, linear algebra is not done by hand. The conceptual stuff is all pencil paper, but the actual computations are done with a computer, numerically. Now, using these normal equations in a computer setting leads to some severe inaccuracy. The errors that you get from round off accumulate, and it just makes the solutions you get useless. So math people, numerical analysts, engineers have all decided we need a better way to solve problems like this. That's going to rely on understanding concepts. That's going to rely on understanding how to write these equations in yet another way. And the alternate form that we're going to talk about is going to be based on the QR factorization we talked about before. So it's going to be based on that. Now, you may or may not remember that in order to use QR, we need a matrix that has linearly independent columns. So if we are going to write this, this requires A to have linearly independent columns. So for the time being, we are going to assume that this is the case. Now, in the problem we worked on earlier, this was definitely the case. We had two columns and they were independent. So we have A with linearly independent columns, and that means that A can be factorized as QR. So now let's talk about what the normal equations would give us. What would they become? Okay, so if I've got A as QR, the transpose is just going to be the transpose of this, which is R transpose Q transpose in reverse order. And that means if I go A transpose A multiplied, I will get R transpose Q transpose times QR. Now, the nice thing about matrix multiplication is that you can insert brackets like this by any two adjacent product. And because Q is an orthogonal matrix, this is something you may need to remember. An orthogonal matrix, the inverse of an orthogonal matrix is just equal to its transpose. That's one of the wonderful properties that they possess. That means this product is equal to just straight I. And what you then have is that A transpose A, which is in the normal equations, is just R transpose R. Now, A transpose times this thing B is just going to be R transpose Q transpose times B. And so the normal equations then end up giving us this. So if we start with A transpose AX hat equals A transpose B, they are going to turn into R transpose RX hat equals R transpose Q transpose B. Now we can do better. This thing is common to both sides. We can basically rewrite this system as follows. And this is the whole point. And that becomes a proposition. We've got a new result that we can talk about. So if the columns of A are linearly independent and A is equal to QR, then you can solve this alternate problem. So then the least squares solution, X hat, is found from this alternate form. R X hat equals Q transpose B. It's easy to solve. We know because the columns are linearly independent, that was a condition that we needed to have to guarantee a unique solution. So if we are in the realm of QR, we're going to get a unique solution. Now, this is nice. R was an upper triangular matrix. That's very easy to solve. Now, admittedly, when you do this kind of stuff by hand, it's going to be problematic because you have to form the Q and the R factorization. But if you want to look at it from a big picture setting, when you form the QR factorization once, you've got it. those matrices will be stored, and then you can just repeat them and apply them over and over again to different right-hand sides B, which is a situation that happens a lot in practice. So in real world, what happens is that you form the factorization once, it costs you something up front, but you can do it ahead of time and you don't have to repeat it for every other problem, which is nice. So just to finish all of this up, I want to show you how that previous example we were working on can be solved using the QR factorization approach. So in order to do this, we need to solve the above system. Rx hat is Q transpose B hat, or sorry, just Q transpose B. So we need R and we need Q transpose. All of this stuff requires us to find the QR factorization. Q we find using our Gram-Schmidt process. In the Gram-Schmidt process, we are going to let the first vector W1 be this, 1, 1, 1, 1. W2 is going to be the second orthogonal vector in this basis. And in order to do that, we need to use projections. Now, before I even begin, I have to make sure that the column vectors I have are linearly independent. Because there's only two of them, it's very easy to see they're not multiples. Therefore, they will be independent. So we're in business here. If I want to find W2, what I need to do is take the second column here, V2, and project it onto the space spanned by this thing. And I will subtract off those two components, just like normal. So remember, this was just a Gram-Schmidt process. And just for clarity, we're going to say that the first column, V1, will be W1, and we go from there. So you may need to review Gram-Schmidt again, but basically the idea is you're forming this projection, and then you subtract it from your original. V1 dotted with itself, you can see, is just 4. You're going to find that V1 dotted with V2 will be 16. So this projection here is going to be V2 minus 4 bunches of V1. And if you sit there and you calculate that, that's going to give you -2, -1, 1, and 2. And as always, you can double check your work by saying, what does W1 dot with W2 give me? Gives me 0 like it's supposed to. So now I have found an orthogonal basis for W, which is the column space of A. It's just formed by these two vectors, W1, W2. So there's W1, and here is W2. But QR doesn't want an orthogonal basis. QR wants an orthonormal basis. And that's going to be denoted by what I'm going to call here U1, U2. The length of W1 is the square root of this quantity here. So that means I'd have to divide everything in W1 by a half. So it would be a half W1. The length of this vector here is root 10. So this second orthonormal basis vector is going to be 1 over root 10 times W2. Q, the matrix Q, is therefore then formed by these two columns, U1, U2, and I will get the following. I will get a half, a half, a half, and a half, because remember, I'm taking the first column and just weighting it by a half. -2 over root 10, 1 over root 10, -1 over root 10, 1 over root 10, and 2 over root 10. There is the set of vectors that forms the orthogonal matrix Q. This is not a square matrix, and that's okay. So I have to be careful. I shouldn't call it an orthogonal matrix. It's a matrix with orthonormal columns. And so here's the idea now. QT, I'm just going to take the transpose of this, and I will get the following. So reminding ourselves that now what we need to do is solve this system. Q transpose B, R, X hat. if I'm going to solve this problem, I need my upper triangular matrix R. And in this case, since I have A is equal to QR, it basically means that Q transpose A is equal to R. And in this particular case, I will be in business. Another way to think of it, again, you might say, well, hold on. How can you do that if your matrix isn't square? There is a property of orthogonal or matrices with orthonormal columns for any Q that's m by n with orthonormal columns. And so that means if I hit both sides of this matrix by Q transpose, this will be equal to the identity. So R is going to be Q transpose A. So I will take it 1/2, 1/2, 1/2, 1/2, negative 2 over root 10, negative 1 over root 10, 1 over root 10, 2 over root 10. I will take my original matrix, put it here. This is a 2 by 4. This is a 4 by 2. I'm going to have to end up with a 2 by 2 matrix. R is an upper triangular matrix. So if I sit there, you can pause the video and do this again. You're going to find that R will be 2, 8, 0, and root 10. Now, just a reminder about what this means. A is equal to Q times the first row, Q times the second row. And that means these, or the first column, sorry. So that means that these two store the weights. That means that the first vector in A has to be the columns of Q weighted by these things. So it's going to be 2 times U1, and then the second vector in A is going to be 8U1 plus root 10U2. That's what those things mean. Again, pause the video, remind yourself about that if you need to. We are finally ready. We can now solve R x hat equals Q transpose B. Q transpose B, if you sit there and you calculate this, 1/2, 1/2, 1/2, 1/2, negative 2 over root 10, negative 1 over root 10, 1 over root 10, 2 over root 10, 3, 2, 1, 0. You end up getting 3 and negative 7 over root 10. Putting it all together, you end up with a nice system that's pretty easy to solve. So R x hat Q transpose B is going to give you this system. It's going to be 2, 8, 0, root 10. You might panic and say, oh, that root 10 is awful. It's actually not going to be bad at all for us. If you row reduce this system, you'll get 1, 4, 3 halves, 0, 1, negative 7 over 10, and you're starting to see that these numbers look familiar. What you end up getting is 1, 0, 0, 1, the good old 43 over 10, the negative 7 over 10, just like before. So you're not supposed to get anything different. You're supposed to get exactly this same result. The point of the story here is that we can come up with the same unique solution using QR instead of using the normal equations. Why do we want to do that? Your teacher's trying to prep you for the future, where you all go on and learn how to do linear algebra with algorithms, and then you'll learn that QR is the way to go to preserve accuracy and to be as error-free as possible.